Specification for Foundation Fieldbus Part. Device information files are essential components of the Foundation Fieldbus ecosystem, enabling standardized integration, configuration, and diagnostics of field devices across a variety of host systems. These files contain the structured digital representation of a device's capabilities, communication objects, function blocks, parameters, and user interface behavior. By using these files, host systems, including distributed control systems, DCS, asset management systems, AMS, and handheld configurators, can communicate with field devices in a vendor-independent, interoperable manner. The primary types of device information files used in Foundation Fieldbus are device description (DD) files, capability files (CFF), device identification files (XDD, XML). Each of these serves a distinct role in enabling full-featured, vendor-neutral integration. The device description, DD, is a standardized text-based file that defines how a host system should interpret the data structures within a Fieldbus device. It describes the layout and behavior of function blocks, transducer blocks, parameters, operational modes, alarms, and supported commands. DDs also include information on units of measurement, default values, data ranges, access rights, read-write, and display formatting, allowing hosts to present a consistent, user-friendly interface regardless of device manufacturer. DD files are interpreted by the host using a DD services layer, which parses the file and presents the appropriate parameter list, graphical interface, and navigation tree. This enables field technicians and engineers to configure, calibrate, or diagnose any DD-compliant device using standard software tools without requiring proprietary software. For example, configuration tools like Emerson AMS or Yokogawa PRM utilize DDs to provide dynamic device views during commissioning and maintenance. Capability files, CFF, complement the DD by defining the device's communication behavior, specifically how many function blocks it supports, the block types, their execution timing, and the scheduling model. The CFF provides the host with static configuration data needed for offline engineering, including VCR requirements, resource capacities, memory allocation, and macrocycle compatibility. It is particularly important for automated segment configuration and resource planning during project design. DD and CFF files are created and published by device manufacturers but must be tested, validated, and registered with the Fieldcom group to ensure conformance and interoperability. Only registered files are accepted by compliant host systems. This registration guarantees that any Foundation Fieldbus compliant host will interpret the device correctly, regardless of the vendor, firmware revision, or specific function block implementation. Device identification files, such as the extended device description, XDD, or XML-based files, are an evolution of the original DD format. These files provide enhanced metadata and are designed for use in modern engineering environments where integration with web services, asset management tools, and enterprise software is required. XDD files support long tag names, multilingual support, and enriched visualization features. Device information files also support parameter grouping and menu structures. Engineers can organize related parameters, e.g., diagnostics, calibration, alerts, into tabs or menus for faster navigation. Help texts, enumerated lists, dependency checks, and input validation logic can also be embedded in the DD to improve user interaction and reduce configuration errors during field operations. To support revision management, each file is tagged with a device revision, DD revision, and functional profile revision. Host systems must maintain a DD CFF library and match these versions during device discovery. Incompatibilities between device firmware and DD versions can result in incomplete parameter visibility or incorrect behavior, which is why strict version control and library updates are crucial during system upgrades or device replacements. All device information files must be provided by the vendor as part of the device supply package. These files shall be supplied in both source format for integration into host systems and compiled binary format if required by the host. The files shall also be documented with clear version history, supported host platforms, and usage instructions. Digital signatures or checksums may be included to ensure authenticity and detect file corruption. In summary, Device information files are the digital blueprints that allow Foundation Fieldbus devices to be integrated, configured, and operated reliably across multi-vendor systems. By formalizing how devices expose their structure and behavior, these files empower automation engineers to deploy scalable, flexible, and interoperable process control architectures with reduced engineering effort and enhanced lifecycle support. Specification for Foundation Fieldbus Part 14, Managing Fieldbus Projects, Planning Phase. The planning phase of a Foundation Fieldbus project is the most critical stage for ensuring the long-term success, maintainability, and scalability of the digital automation infrastructure. Proper planning requires a holistic approach that integrates process requirements, instrumentation strategy, control system architecture, communication infrastructure, and lifecycle support. Unlike traditional 420 mA systems, Foundation Fieldbus introduces distributed intelligence, shared media, and deterministic communication, factors that must be explicitly addressed during project definition and front-end engineering design, FEED. The first step in the planning phase is the definition of project scope and objectives. This includes identifying which process areas will use Foundation Fieldbus, the types of measurements and control loops involved, safety and criticality classifications, and integration points with legacy systems. A clear scope ensures the project team can determine the appropriate balance between Fieldbus and other protocols, e.g. HART, Profibus, Modbus, and apply digital field technology where it adds the greatest value. Device selection strategy is a key planning task. Engineers must identify Foundation Fieldbus capable instruments that meet both process and communication requirements. This includes evaluating function block types, diagnostics capabilities, power consumption, compliance with IEC 16158 standards, and FieldCom group registration. For standardization and maintenance efficiency, the project should limit the number of device types and vendors while ensuring interoperability across the system. Network segmentation and topology design is central to planning. Engineers must define how many H1 segments will be used, how many devices will be on each segment, typically no more than 12 to 16, and whether a flat or hierarchical structure via linking devices or HSE is most appropriate. The topology, tree, star, or daisy chain, must account for trunk and spur lengths, grounding, segment redundancy, and hazardous area classifications. Careful planning of these aspects prevents communication delays, voltage drops, and overloading of power supplies. A macrocycle strategy must also be considered early. Since Foundation Fieldbus uses scheduled communication for function block execution, all process control loops must be analyzed to determine appropriate macrocycle times, e.g. 500 milliseconds for slow loops, 100 milliseconds for fast loops. These timing parameters will affect the number of function blocks per segment, the complexity of the schedule, and the assignment of execution times across devices. Power and intrinsic safety design is another planning essential, especially for hazardous area installations. Engineers must determine if conventional FISCO, FNICO, or entity models are to be used and size power conditioners accordingly. Device current consumption, cable impedance, and segment termination must be calculated to maintain compliance with voltage and current limits while ensuring stable operation. Where necessary, field barriers and segment couplers must be specified and their locations integrated into the layout. Integration with host systems requires early coordination between the control, instrumentation, and IT teams. Host systems must support Foundation Fieldbus standards natively, including system management, device diagnostics, function block configuration, and DDCFF interpretation. The planning phase must confirm compatibility of host DCS hardware, Fieldbus interface modules, FIMs, and asset management platforms with the selected device models and firmware revisions. Spare capacity and future expansion must be factored in. Segments should be loaded to 60-70% of their maximum capacity, allowing for future device additions without re-engineering. Control cabinets, cable trays, power supplies, and switch ports should be provisioned with space and capacity to accommodate growth. This foresight ensures that expansions can be achieved with minimal disruption. Tagging, documentation, and addressing policies must be established during planning. Each Fieldbus device, block, and segment should have a unique, traceable identifier that aligns with plant standards. A consistent approach to node addressing, PD tags, and block indices will simplify commissioning, troubleshooting, and long-term support. Standard naming conventions for junction boxes, cables, and segment layouts are essential for field clarity. Finally, the planning phase must result in a comprehensive engineering deliverable set, including segment drawings, device lists, function block schedules, I/O allocations, power budgets, voltage drop calculations, network load analysis, and configuration databases. These documents form the blueprint for the next project phases: design, installation, commissioning, and operation, and are critical for risk reduction, procurement alignment, and schedule control. In conclusion, successful Foundation Fieldbus implementation begins with disciplined and structured planning. By addressing technical, architectural, and operational considerations up front, project teams can leverage the full benefits of Fieldbus: enhanced diagnostics, reduced wiring, distributed intelligence, and long-term scalability, while avoiding the pitfalls of poor segmentation, improper loading, or inadequate configuration strategies. Specification for Foundation Fieldbus Part 15 Teen. Managing Fieldbus Projects Installation Phase. The installation phase of a Foundation Fieldbus project is where the physical infrastructure, cabling, devices, cabinets, junction boxes, and network components is brought to life. This phase must be executed with a high degree of precision and adherence to Fieldbus-specific standards to preserve signal integrity, ensure device functionality, and maintain the deterministic communication required for distributed control. Foundation Fieldbus installations differ significantly from conventional analog wiring, particularly in aspects such as shared bus segments, power conditioning, and signal shielding. The first step in the installation phase is the preparation and verification of installation materials. All components, Type A, shielded twisted pair cable, terminators, junction boxes, field barriers, segment couplers, and device mounting hardware, must be confirmed against approved specifications and drawings. Cables must be inspected for continuity, correct labeling, and compliance with insulation, shielding, and capacitance requirements per IEC 61158-2. Only approved and tested components shall be deployed to the field. Trunk and spur cabling must be installed with care. The trunk, which carries both power and communication signals, runs from the control room or marshalling panel to junction boxes in the field. Spurs connect individual devices to the trunk. Installation must observe strict maximum lengths, typically 900 meters for the trunk and up to 120 meters cumulative spur length depending on device count. Cable trays and conduits must avoid running parallel to power cables, and minimum separation distances must be maintained to reduce EMI exposure. Cable terminations must be done meticulously to preserve signal quality. The cable shield must be grounded at one point only, usually in the control room, to prevent ground loops. Drain wires must be properly dressed, not left floating, and connected to designated terminals. Overstripping of cable insulation must be avoided, and all terminations should be crimped or soldered per manufacturer recommendations. In intrinsically safe areas, cable entries into junction boxes must be flame-proof and compliant with area classification requirements. Each segment must include exactly 2 terminators, one at the host or power supply end and one at the farthest junction box. These must be 100 ohm resistors in series with 1 μF capacitors installed in compliance with the physical layer requirements. Incorrect termination, too few or too many, can result in reflections, signal distortion, or complete segment failure. Technicians must verify and document terminator locations and resistance values before proceeding to energization. Device mounting and mechanical installation must conform to process area standards, especially in hazardous locations. Devices must be installed in accordance with their XDEXI or EXN certifications, using approved cable glands, mounting brackets, and orientation constraints. Junction boxes should be installed within reach with labeled terminals and sufficient space for future device additions. Spur connections must be clearly labeled, secured, and protected from mechanical damage or vibration. Power conditioning equipment, including isolated power supplies, field barriers, and segment couplers, must be mounted in well-ventilated enclosures with adequate spacing and grounding. Each segment power supply must be sized to support the total device current with at least 20% margin and include short circuit and overvoltage protection. Isolated supplies must provide impedance insertion as required by the signaling standard. Grounding and shielding must be implemented following IEC guidelines and vendor instructions. All device and cable shields must be bonded to a single ground reference. Cabinet, cable tray, and device grounds must be tested to confirm resistance values within specified limits. Floating shields or multiple ground points can induce noise and disrupt deterministic communication. Once physical installation is complete, pre-commissioning checks must be performed. These include continuity tests on all cable segments and spurs. Resistance checks across terminators should read approximately 50 ohms. Isolation testing between conductor and shield ground. Visual inspection of terminations. Labeling and cabinet layout. Verification of device polarity, integrity of cable dressings, and proper enclosure sealing. A segment loop diagram must be marked up and updated to as installed status. This includes cable routes, junction box locations, device addresses, terminator positions, and power supply identification. These records are essential for future maintenance and troubleshooting. Documentation of the installation phase shall include completed checklists for cable testing, grounding and shielding test records, device installation reports with serial numbers and tag references, photographic evidence of cabinet interiors and junction boxes, updated layout drawings and segment maps. In summary, the installation phase is critical to preserving the electrical and logical integrity of the Foundation Fieldbus system. Strict adherence to best practices for cable handling, grounding, termination, and environmental protection ensures that the segment will support reliable, noise-free communication once commissioned. Proper planning, skilled execution, and thorough documentation during installation directly contribute to the long-term success and maintainability of the Fieldbus infrastructure.